Hello, welcome to CSC 8025, Computer and Network Security. My name is Brady Chen. I'm from Department of Computer Science at Fitchburg State University. So the course consists of many modules which cover the fundamentals of number theory, authentication and encryption and decryption technologies, as well as some of the well-known security-related topics. And it also covers some well-known encryption and decryption algorithms widely used in industries. Okay, Module 2, Classical Encryption Techniques. Now, the classical encryption techniques can be traced all the way back to the Roman Empire. Now, there are two basic techniques. One is the substitution, and the other one is the transposition. And we will talk about these two later. Okay. The earliest known use of a substitution cipher was by Julius Caesar. Okay. So many of the ciphers used during the World War II are also regarded as the classical encryption techniques. Okay, so in Module 2B, we're going to continue to discuss the classical encryption techniques. Okay, and we'll talk about the operation of a polyalphabetical cipher. In particular, we're going to talk about a play-fair cipher. And then at the end, we're going to also talk about the Hill cipher, which basically use the matrix to perform the encryption and decryption. Okay, so now let's talk about a play-fair cipher. Now, play-fair cipher is best known as the multi-letter encryption cipher. Now, it was invented in 1854, by British scientist Sir Charles Wheatstone. Okay. Now, the play-fair cipher has been used as a standard field systems by the British Army in World War I and has been widely used in World War II. Okay. Now, play-fair cipher treats diagrams in the plain text as a single units. Okay, so that means for the original plain text, we're going to group the original plain text into units, and each unit contains 2 characters, and then we translate these units into cipher diagram. Okay, so now the play-fair cipher is based on the use of like a 5x5 matrix, okay, of letters constructed using the keywords. Okay, now let's take a look at the example in the next slide. Okay, so in this slide, we're going to actually talk about an example of the play-fair. Okay, so the most important step in the play-fair encryption algorithm is to create a play-fair key matrix. Okay, now before we do this, we need to select a secret keyword, a key. We need to select a key. In this case, we're going to select the key monarchy. Okay, and then we're going to start to fill the matrix, fill the 5x5 matrix from left to right, from top to the bottom. Okay, so but we're going to start with the keyword. Okay, so we're going to fill the 1 position with the first letter M, which is the first letter in the keyword, and then the next position we're going to fill the O, then N A R C H Y. Okay, so we actually first fill the keyword into this 5x5 matrix. Now for the remaining actually positions, we gonna fill the letters alphabetically from the very beginning, A, B, C, D, all the way to X, Y, Z. But first, when we fill this letter, we need to check whether the letter has been used in the keyword. Okay, so the first letter is A in the in the alphabet. So, but we first need to check whether A has been used in the keyword. Okay, now we find out A is in the keyword. So we're going to skip the A and we check B. And then we find out B is not in the keyword. So then we fill B in the next position. And then we're going to check the C, right? Now, again, we need to check C whether C is in the keyword. And yes, C is in the keyword. So we skip key and check the next letter, D. Okay. So then we find out D is not in the keyword. So we fill the D. And then the next one we're going to fill is E, F, G. Every time when we see a letter appears in a keyword, we skip it. Okay. Now, the problem with this playfair is now we have a total of 26, letters in English from A to Z, right? The matrix is 5 by 5, which contains total of 25 positions, 25 slots. So somehow we have to actually fill 2 letters in one position, right? Now, typically we're going to choose I and J. Why? Because both I and J are less frequent letters in the English paragraphs. Okay, so typically we're going to actually combine the I and the J in one position. Okay, so let's actually continue to fill the matrix. So we have a B, D, E, F, G, and H. H is actually in the keyword. So then we fill the I and the J. Okay, and then we're going to fill K, L, P, Q, S. Every time when we see the letter which is actually appear in the keyword, then we skip it. So eventually we actually completely fill up the matrix. Now that's the playfair key matrix. Now in the next slide, we're going to talk about how we going to actually encrypt the plain text. Okay, so once the playfair key matrix is built, then we need to follow the steps or procedures to encrypt the plain text message. Okay, the first thing we need to do is we need to group the plain text letters into units of 2 letters. Okay, let's do this. Let's suppose we have a plain text message. Balloon, B-A-L-L-O-O-N. Okay, so we need to actually group the plain text letters into units of 2. Okay, so let's say first unit is B and A. Okay, now the second unit supposed to be L and L, but based on the first rule, so repeating plain text letters that are in the same pair, in this case you have 2 L's. So in this case, repeating plain text letters that are in the same pair are separated with filler in the letter. Now, typically, we're going to use letters like X, Y, or Z that are less frequently used in the English paragraph as a filler. Okay. So in this case, so we have to separate the 2 L's into different units. Okay. So we need to filler X. So let's regroup this original plain text. So the first unit is BA. So the second one, we're going to group L and the filler X. Okay, so that's a second unit. Now the third one is L, O, right? And then O, N. Even though we have 2 O's, but these are not, repeating plain text letters because these 2 O's are, basically separated into 2 units. So we don't need a filler in this case. Now, once we're done this, then we're going to follow the next couple of steps to encrypt the message into the ciphertext. Now, second one, so that's the first one. This is the second rule. So we're going to check each pair, okay? So if two plaintext letters that fall in the same row of the matrix are each replaced by the letter to the right. Okay, now this is actually, these letters gonna be ordered in a circular way, with the first element of the row circularly following the last. Okay, that's, we talk about if two actual letters in a unit are actually basically fall into the same row of the matrix. Rule number 2 gonna apply. Now, suppose if we have two letters in a unit, now if these two letters that fall into the same column, then each replaced by the letter beneath, with the top element of the column circularly following the last. Okay, so that's basically the rule. Okay, so basically if you have a letter and then we find out there's no letters beneath it because that's the last, the letter in the last row. So the letter beneath these matrix is not there. So then we need to do the circular way. We need to go all the way to the top. Okay, as the next one. Now, that's rule number 3. Now, rule number 4 is basically the typical case. So if like each plain text letter in the pair, it should be replaced by the letter that lies in its own row and the column occupied by the other plain text letters. So in this case, if two actually letters in the unit, they're not in the same row, not in the same column, so they basically form some kind of rectangle. So then we can actually fill the we choose the letters that are in the other two corners of the rectangle. So let's take a look at this next slide. Okay, so here's an example. Suppose we want to use the playfield key matrix. We want to use that key matrix to encrypt the plain text "Hello everyone." Now, based on the rule, we're gonna actually first group the plain text, into units, right? So HELLO everyone. So then we just group them. So the first group is HE, and then the next one is L2Ls because these are repeating letters. So we need to actually provide a filler. So let's the first L group with a filler X, and then the L group with O, and then E group with V, and ER, YO, and NE. Okay, that's the first step. We're going to group them into units of 2 letters. So okay, so we have done the first step. Okay, we group the original plain text into units. Okay, let's see that what the units are: HE, LX with the filler X, and then LO, and then EV, ER, YO, and NE, right? We just did this in the previous slide. So now let's do the encryption based on the second, third, and the fourth rule. Okay, so let's take a look at the first pair, H and E. So H is here, E is here. So they are not in the same row, not in the same column. So the last rule number 4 gonna apply. So each plain text letter in the pair is replaced by the letter that lies in its own row and the column occupied by the other plain text letter. Okay, lies in the own row and own column. Okay, so then we can actually replace HE with C and F. Okay, let's take a look at the second pair, L and X. So L is here, okay, X is here. So basically we're going to, so technically we can do this. You can think L and X basically create a matrix, right? And L and X basically occupy the two corners, and then the ciphertext is going to be on the other two corners. Okay, so the first is the raw X, and then U. And then we have a LO, so then we have a P, because L is here, O is here. So we can replace L with P and O with M. Okay, now where's EV? E is here, V is here, so you're going to replace E with F, and V with U. Okay, ER, so we're going to replace E with K, replace R with M. Okay, YU, okay, or YO, so we'll replace Y with H, O with N, okay, and NE, so N here, E is here, so N with M, and E with G. Okay, so this is basically the ciphertext. So in this case, none of the letters in a unit basically are on the same row or on the same column, so the encryption should be very straightforward. Okay, just like this. Okay, so here's the summary of the previous example. Okay, now this is the plain text which has been grouped into units. Now the repeating letters, like in this case L, in the same unit has been separated in with a filler. In this case it's X. So then 2L is going to be in the separate units now. So the encryption is very straightforward. Since none of the letters in the unit are located in the same row and the same column, so basically the rule number 4 applied to each of the unit. Now let's take a look at another example to see when 2 letters are in the same row or the same column, what we're going to do. Okay, take a look at this example again, balloon. Remember when we group these letters, BA going to be in the same unit. L, we have to put the filler in there to separate the repeating L, right? So one L is in the first, in the second unit, and the other L is going to be in the third unit. Okay. There's no filler required between O because O has been separated already. Now let's actually apply the rules. Okay, so BA, so let's say B is here, A is here. So these 2 letters are in the same column, right? So based on the third rule, each letter going to be replaced with the letter beneath it. Okay, so letter B going to be replaced with either I or J. So let's say I'm going to put the I. You're going to say, why not J? You can also put the J. It doesn't matter. The reason for this is because I and the J are less frequently used letters in the English paragraph. If something, if you resolve all the other words, and then you can easily figure out whether this is actually I or J. So let's see, B replaced with I and A replaced with B, right? Because the letter beneath A is B. LX, okay, LX. So L going to be replaced with S, X going to be replaced with U, okay. LO, where's O? O. So L going to be replaced with P in the same row. O will be replaced with M, also in the same row as O. ON. So O, and these two letters are on the same row, right? So based on rule, which is rule number 2, so O going to be replaced the letters on the right. Okay, so O going to be replaced with N, and N going to be replaced with the letter on the right, which is A. So that's the ciphertext. Okay, so in this case, B and A, O and N are on the same column and the same row. Okay, so the next question is Playfair safe or secure? Now definitely the frequency of a letter never gonna apply to the Playfair, because Playfair never actually convert one letter to the other. So it's basically use two letters. Okay, so the frequency with one letter never applies to the Playfair. However, the Playfair basically use the letter pairs. Okay, so now if your actually paragraph is long enough, so somehow we can still build the frequencies of bigrams. So that means the frequencies of two letters. So basically what we're going to do is you're going to actually figure out what's the frequency of AA, what's the frequency of AB, frequency of AC, frequency of AZ, and then BA, BZ, BB, BC, until to the last moment, say XA, XB, or eventually XZ, and and the last letter ZA, all the way to ZZ. Okay, so we can actually check the frequency of each of the pairs of letters, the diagrams. Okay, so once you build the frequency, for these diagrams, then somehow we can still figure out, if we have a ciphertext, then we can compare the two letters, the frequency of two letters, and try to figure that out. So even though it's possible, but it's still it's much more difficult to use the frequencies than the for example than the mono alphabetical ciphers, because mono alphabetical cipher just need to build the frequency for 26 letters. But this time, if we want to build the frequencies for the diagrams, then you need to build the frequency numbers for total of 26 times 26. That's a big number, right? So now the diagram here basically shows the relative frequencies of occurrence of letters. Okay, now for the plain text, the letters with the highest frequency, if the letter with high frequency is 1, then the net letter with next frequency is probably 0.9. So then for the total of 26 letters, the frequency diagram looks like this. Okay. Now, Visionaire is like this. It's a little bit flattened because the highest frequency is lower and the lowest frequency is higher. Okay, so that means they are kind of balanced. Now the ideal case is we want to build an encryption algorithm so to make the frequency of the letters are all the same. So in this case, the frequency actually cannot used to actually attack any kind of a ciphertext. So this is the ideal case. Okay, so most of the encryption algorithms, they basically somehow, flatten these frequency curves. Okay, so it's actually closer to this, the straight line, but still, you can still use the frequencies to attack them, even though it's more difficult than the monoalphabetical case. Okay, so let's talk about Here cipher. Now, Here cipher was developed by mathematician Lester Hill in 1929. Okay, it was regarded as a strong cipher at the time because the strength of the Here cipher is that it completely hides the single letter frequency. So it's definitely much stronger than the monoalphabetical cipher. Okay. Now, the Here cipher use the large matrix to hide more frequency information. For example, if we use a 3 by 3 matrix, so that the 3 by 3 Here cipher hides not only single letter, but also two letter frequencies, the frequency of diagrams. Okay. Now Here cipher is strong against the cipher-only text attack. Okay. But the weakness of the Here cipher is that it can be easily broken with non-plain text attack, because with a non-plain text attack, you can basically find based on the inverse matrix of the key. Okay, so then you can eventually identify the original matrix. Okay, so the Here cipher use matrix operation modular 26, which is the number of letters in English language. Okay, so in Here cipher, we're going to actually select a matrix key. It's an m by m matrix. So we're going to talk about a matrix of m by m. Now that's the matrix of integers. Okay, so then we basically find the inverse of this matrix. So the first we find the key, the matrix, K, which is the key, and then we find the inverse of the matrix. Now, but it's also the inverse under modular operation, because typically if you don't use the modular operation, any extra inverse, even though all the elements of the matrix are integers, but the inverse matrix basically contains all the fractional number. Okay, so if we use the modular operation, then the inverse matrix is also a matrix of integers. Okay, now once you actually create the key, which is m by m matrix, and we find the inverse of the key, and then the encryption and the decryptions are relatively easy. So the encryption gonna be like this. So suppose we have a plain text as a row vector, so which is actually the numbers as a row vector. Or we can think about row vector as a 1 by m matrix. Okay, one row and m columns. Okay, so then we multiply p by k and the modular operation. So C is p times k. So p is 1 by m k is m by m. So eventually we're going to generate a c, which is also m1 by m, which is a raw vector. So that's the encryption. The decryption is basically, it's also the raw actually times the inverse matrix. Okay, it's a raw vector times the inverse matrix. So hopefully we can restore the back to the plain text. Okay, let's take a look at the example of a here cipher. Okay, so we actually choose the plain text called pay more money. Okay, now the first thing we need to do is, because here cipher only work with numbers, decimal number or binary number, it doesn't matter. Let's use the decimal number. So the first thing we need to do is encode the original message plain text into sequence of numbers. Now we can do encode the text with various different techniques. The widely used one is called ASCII code, right? So you can easily encode the English letters into numbers. So this is the actually encoded code we have. Okay. So P converted into 15, A is 0, and Y is 24. So we can actually encode each of the letter into a number. So then we select a key, which is a matrix. Now in this case, we use 3 by 3 here cipher. Okay, so which means that the key is 3 by 3 matrix. Okay, now then the next thing is we need to actually find out the inverse matrix of K. Now what's the inverse of matrix? Inverse matrix is the matrix such that you multiply the matrix with the inverse, then the first one is 3 by 3, the inverse is also 3 by 3, and then when you multiply, you will eventually get the identity matrix. It's a 3 by 3 with ones on the diagonal, okay, and a 0 on the rest of the positions. Of course, once you multiply these k and the k inverse, you need to actually perform the modular operation. It's a modular 26. Okay, so then we got this. So now assume this is true. We can easily verify, but no, I did not do the verification here. Okay, so then we first verify k and the k inverse are k to the minus 1 are inverse to each other. Okay. Now to encrypt the plain text, we're going to divide the plain text into block of 3 numbers, because we're going to multiply the block of 3 numbers. That means it's a 3 number the vectors, because we're going to multiply this vector with the matrix. The matrix is 3 by 3, so the vector should be 1 by 3. So it should be 3 numbers. So we're going to divide this into 3, 3, 3, the block of 3, and we call this P1, P2, P3, and P4. Okay, so the first one, P1, is 15, 0, 0, and 24. Now to encrypt it, you need to multiply P1, okay, which is 15, 0, 0, 24, by the matrix K, which is this. So it's a 17, 17, 5, 21, 18, 21, 2, 2, 19. So you multiply, and then, okay, you will get the result. The first the raw P1 multiply with the first column. You multiply the first in the vector with the first in the column, and the second with the second one, third in the vector multiply the third one in the column. So based on the calculation, we know that the answer is 303. Okay. So basically it's a 15 times 17 plus 00 times 21 and 24 times 2. So that's the first one, which is 303. And the second one, this vector multiply the second column pairwise. 15 times 17, 0 times 18, and 24 times 2. So we got the same number. Okay, so that's the one is 531. So 15 times 5, 0 times 21, and 24 times 19, right? So you got the 531. And then each of these gonna do the modular operation. So that means the first one, 303 divided by 26, and then the remainder is 17. And 303 divided by 26, the remainder is 17. And the 531 divided by 11, divided by 26, the remainder is 11. Okay, so that's the final answer for this. And then, so we got the C1, right? So it's a 17, 17, 11. And then we're going to do the P2. So let's say C2 equals P2 times K modular 26. And then we get the answer. Okay, modular 26. And then we got the answer. So we can record the next three numbers. And then we're going to do this for P1, P2, P3, and P4. So we got a sequence of numbers. Now that's the ciphertext. Okay, so the first one is C1. Now the decryption is relatively straightforward. So in order to recover the P1, so you need to multiply C1 by the K inverse, which is the second matrix. Okay, so modular 26. So so that's the decryption side. So you need to actually get the ciphertext and then multiply with the inverse of the key, which is k to the -1. Then you got the plain text. You do this for each ciphertext block, C1, C2, C3, and C4. Okay, so that's the here cipher. Okay, so now the next techniques we can talk about is the polyalphabetic ciphers. So the polyalphabetic substitution cipher basically improves on a simple monoalphabetic techniques by using different monoalphabetic substitutions as one proceeds through the plain text message. As you can see that in the monoalphabetic ciphers, we map each of the letters with the other letters. So that means for each letter, A, B, C, we're gonna actually shift, certain position to the right. But however, if for every actually A, we're gonna shift the same amount. For B, we're gonna shift the same amount. But however, with polyalphabetic, so then even the letter A, you're gonna shift to a different positions, depend on the position of the A in the plain text. Okay, so let's see that all these techniques basically have the following features in common. Basically, we have a set of related monoalphabetical substitution rules used, and also we use the key. A key determines which particular rule is chosen for the given transformation. Okay, now let's take a look at the. Okay, so let's talk about the Vigenère cipher. Vigenère cipher is one of the simplest polyalphabetical substitution ciphers. Okay, now in the Vigenère ciphers, the set of related monoalphabetical substitution rules consists of the 26 Caesar ciphers with shifts of 0 through 25. Okay, now each cipher is denoted by key letter. So we need to choose the key letter, which is the ciphertext letter that is substitute for the plain text A. Okay. Let's take a look at the examples. Okay, so let's take a look at the example of a Vigenère cipher. Now, Vigenère cipher need a key. Okay, a key is needed. That is as long as the message goes. So, for example, if the message contains 1 million characters, okay, so now we need a key of 1 million characters as well. Okay, now this is not really realistic in most of the case. So in most of time, people don't choose a key as long as the message goes. People normally choose a small key but repeat that small key. Okay, so here is an example. So let's say we have a key called a deceptive, the keyword. It's a deceptive. And the message word we try to actually encrypt is this. We are discovered. Save yourself. Message is short, but at least it's longer than the keyword, right? So we need to actually, repeat the keyword deceptive. Okay. So we actually organize the plain text into the block of the size of the key. Okay. So the key deceptive, deceptive, deceptive. Now the first key corresponds to the first plain text letter. The second key letter corresponds to the second plain text letter. And so we continue to move forward. Then we have the match. As long as the plain text goes, we repeat the key. So make sure each plain text letter will be corresponding to one of the letter in the key. Okay. So the key actually repeated 3 times. Now here's the beautiful part of the Vigenère. So typically in the monoalphabetical, so normally each letter will be associated with the same key. Okay, A is going to be mapped to one particular letter, so that's the key for A. B mapped to another letter, and that's the key for the B, right? But in this case, the plain text W, if it's the same W, gonna actually basically gonna be mapped to a different keys, depending on where the W is, depending on the location of the W in the plain text. Let's take a look at this. Okay, so let's say the key is deceptive, right? Now, remember in the previous presentation, I think in module 2A, we mentioned that using the mapping, so each letter A, B, C, D is corresponding to a key, right? A is mapped to 0, B is mapped to 1, C is 2, D is 3, E is 4, and then Z is actually 25. Y is 24, X 23. So that key D is actually corresponding to the key number 3, E is key number 4, and C is key number, let's see, C is 2, yeah, C is 2, and E is 4 again. P is, I don't know what this P is, so that's 4. Okay, so let's take a look at the first 4 numbers. So W, E, A, R. Okay, so W, when you use W, and so remember, for each letter, we're going to use the Caesar cipher. And the key for the Caesar cipher is defined by the key. So, when you actually encrypt the W, we're going to use the key 3. So basically for W, we're going to actually choose the letter which is 3 position on the right. So let's say W, X, Y, Z, right? So position 1, 2, 3. So we map W to Z. Why Z? Because the key is 3. Now, the next letter is E, okay? The plain text is E. So when we map E, so what's the cipher character? So E gonna actually move 4 positions towards the right, okay? So let's see, because the key is 4 in here, corresponding to E. So then we have E, F, G, H, I. So that's 1, 2, 3, 4. Okay, so it's I. And then we can see that the C is the key for the third letter, which is A. Okay, so when we actually using the Caesar cipher, the key is 2, for A. So then we got a C. So that means if we randomly choose any letter, let's say we want to, encrypt the letter O, and then we check the key, which is 3. So then the cipher text character is R, because you're gonna shift it, 3 positions towards the right. So O gonna map to R. Okay. So that's basically the idea for the Vigenère cipher. Vigenère cipher, you have a key string, okay, typically use the short key and repeat itself, and then we can actually map each of the letter in the alphabet based on the corresponding letter in the key. Okay, so one of the variation of the Vigenère cipher is the Vigenère auto key system. Okay, now the difference between the Vigenère cipher and the Vigenère auto key system is that the Vigenère use the key and repeat the key. Okay, but now in Vigenère auto system, you basically apply the key initially, and then you basically, follow the plain text, okay, as the running key. So first use the actually secret actually key, and then we don't repeat the key. Instead, we use the plain text afterwards. However, now this scheme is still vulnerable to cryptanalysis because the key and the plain text shares the same frequency distribution of the letters. So the statistical techniques can still apply, even though it's still much better than the monoalphabetical, right? Yeah, a little bit better than probably Vigenère cipher, but it's vulnerable. Now, the best way to apply the Vigenère cipher is to use the table. The table, okay? So in this table, we're gonna actually, list the 26 alphabet A, B, C, D all the way to X, Y, Z in the first row, and also in the first column, we also list the A, B, C, D. So then in each row, we're gonna actually do a slight shift to the left. Okay, so the first row, we don't have any shift. The second row, we shift each letter to the left 1 position. Now the first letter A, because there's nothing on the left anymore, so the first letter A gonna be, circularly placed at the end of the second row, and then B gonna be in the first position. Now C gonna be in the second position, and then we shift again to the left 1 position. So we keep doing this. So we build this particular table. Okay. Now, how can we encrypt the message? Suppose we have a plain text. We are discovered. Please save yourself. Okay. So, as we see that, for the first plain text W, okay, the key is D, right? Now, how can we use that table? So basically what we're going to do is we're going to first look at the first column and then find the letter D. So A, B, C, D. Okay. Okay, that's the key, right? And then on the first row, we're gonna find the plain text W. Okay. So now we're gonna follow the intersection of D and W, and then we locate the letters Z. So that's the ciphertext. Okay. Now let's pick another one. For example, let's say V. That's the key, right? The corresponding plain text is S. So what we're going to do is find the V, which is the key, and then find the S over here. And then we try to find the intersection of V and S, which is N. Okay, so that's the ciphertext. So now we basically use the table to make the Vigenère cipher just simply as a table lookup. You know, this is a very simple way to do this. And also, if you want to write the code for these Vigenère cipher, the code basically just programmed in a way that for the encryption, you just actually have this table lookup and find the ciphertext. Okay, so let's talk about the Vernon cipher. The Vernon cipher basically applies to the string of binary numbers. Okay, let's suppose we have a plain text, which is actually a binary sequence. That's a plain text. Now, corresponding to the plain text, we need to actually provide a key. It's called a key string, which is also a sequence of binary number. Let's say key string is 10111111. Okay, so that's a key string. Now, the operation is pretty simple. We can actually provide the operation called exclusive OR. It's an exclusive OR operation. Now, the definition for the exclusive OR operation is pretty simple. Okay. So suppose I have, the binary number 0 and 1, 0 and 1. Now, if I actually play the exclusive OR, or sometimes we use this, plus with the circle. So when both, when both bits or the binary numbers are the same, the exclusive OR gonna give you 0. If they are different, they will give you 1. Okay, so for example, 0 exclusive OR 0 is 0. And 0 exclusive OR 1, because these two numbers are different, it gives you 1. And the 1, 0 is 1. 1 exclusive OR 1 is also 0. So in this case, it gives you this table. 1, 0 exclusive OR 0 was 0. 1 exclusive OR 0 is 1. And 0 exclusive OR 1 is 1. Okay, so that's a table. So based on this, so if you already have the key string and for the plain text, you can perform the exclusive OR operation between the plain text bit and the key string bit. So for example, the plain text is 1, the corresponding key string is 1, then you can have a 0. Because by exclusive OR operation, these two numbers are same, so you got a 0. And a 1, 0, you got a 1. 0, 1, you got a 1. 0, 1, 1, you got a 0. 0, 1, you got a 1. 1, 1, you got a 0. Got a 0, 0. So that's the ciphertext. Okay. So you have a plain text string and a ciphertext, key string. Okay. Now, So the key for the Vernon cipher is how can we generate the key string? The key string should be as long as the plain text string. Okay. Now this is very similar to the Vigenère cipher, right? But in this case, the string is actually the binary string. Okay. So the key point for the Vernon cipher is the key generator. That's very important. How can you generate the key? Okay. Once the key is generated, you got a key string. The encryption itself is pretty simple. And also decryption is also very simple. Why? Because if you already get the cipher text, like a 011010000, like this one, right? And then the key is already known, so that's a cipher text. The key string is already known. So 10111111, right? Yeah, 101111. So now the decryption basically use the same technique. It's also the exclusive OR operation. So that means you have a ciphertext 0, key strings 1, then using the exclusive OR operation, you got 1, and then you got a 1 again, you got a 0, you got a 1, you got a 0, you got a 1, 1, 1. So you can compare these with the original message, plain text. It's the same. So once you got a key string, the encryption basically performs the exclusive OR between the plain text and the key string. The decryption also plays the exclusive OR between the ciphertext and the key string. So it's the same operation. Okay. Now the question is, how secure the Vernon cipher going to be? The answer lies in the key string. How random the key looks like. Okay. The more secure the key, the more secure the algorithm. Okay. The cipher. So one of the improvements to Vernon ciphers is proposed by an Army Signal Corps officer, Joseph Morgan. Okay, he basically used a random key. It's called a one-time pad. Okay, use a random key that is as long as the message, so that the key need not to be repeated. Of course, if the key is completely random, okay, then that's the safest cipher. Okay. Now, once the key is used, then it will be discarded. Next time when you do the communication, we're going to generate another key, which is also random. Okay, that's called a one-time pad. Okay. So each new message requires a new key of the same length as the new message. Okay. Now, theoretically, one-time pad is unbreakable. Okay. It's completely random, but it's also very difficult to perform, because the key point, the most difficult part is once you have a very extremely long key, then the distribution of the key is a big challenge for this. Okay, so in most cases, people don't use one-time pad, but unless in extreme case. Now, what's the challenges with the one-time pad? The one-time pad offers a complete security, but in practice, there's two fundamental difficulties. One is that there's a practical problem of making large quantity of random keys. Okay, how can I generate these random keys? And any heavily used system might require millions of random characters on a regular basis, because if you want to communicate, a lot of actually messages on a regular basis, like every day, then it's a big challenge to generate large millions of random characters. Now the second one is the distribution of the key, as we mentioned in the earlier slide, because the key itself is the same size as the message itself. the distribution itself, the key of itself is equally difficulty as the distribution of the plain text. So that's the reason why the one-time pad is of limited utilities. Normally, only in the extreme case, then normally people don't use it. Okay. Okay. So now the next cipher we're going to talk about is called the rail fence cipher. Okay. It's the simplest transposition cipher. So in this case, we don't use the substitution. We don't replace anything, but we reshuffle the message. Okay. So in this case, for example, if we want to send a message like, for example, meet me after toga party. Okay. So then we're going to reorganize the messages into two rows. So first we place them M, and then we're going to put the the second one in the second row, but shift one position, and then next one MEET, meet me after, okay, AFTER, the toga party, PARTY. Okay, so you're going to read this mesh, organize the message that way. So into two row, and the second row we did the shifting. Okay, and then we're gonna actually send a message as, first row and the second row. So then we have a ME, MA, TR, and T. So that's the message we send out. Now, if the receiving side knows that trick, they can easily restore back to the original message. Okay, so it's basically a very simple transposition cipher, which does not change any letter but reshuffle it. Now here is a more complex transposition cipher. Okay, it's called a raw transposition cipher. Now in this case, we actually gonna organize the plain text into some kind of matrix. Okay, so in this case, the plain text is like this: attack, postponed, until 2 a.m. XYZ. No, that's the original message. And then we organize the message into a matrix of, let's say 4 by 1, 2, 3, 4, 4 by 7. Okay. Okay. So we organize this from the left to the right, from top to the bottom. So attack, postponed until 2 a.m. XYZ. Okay. And then the key we're going to select is a sequence of decimal numbers. Okay. So key going to be 1, 2, 3, 4, 5, 6, 7, 7 numbers. But we actually reshuffle the number. So it becomes 4, 3, 1, 2, 5, 6, 7. So we can reshuffle these. And then the cipher text is going to be read like this. Okay, so we first read this, the column with number 1. And then we're going to read the text from top down. So T, T, N, A. So T, T, N, A. And then we read the second one, A, P, T, M. And then we read the third one, T, S, U, O. And then read the fourth one. So we can just keep actually read next columns based on the numbers defined by the key. Okay, so that's the ciphertext we actually got. Again, once the receiving side, if the receiving side knows the key, they can actually rebuild these messages based on this pattern. Okay, that's a raw transposition cipher. Okay, I think that's pretty much all we're going to talk about in module 2B. Okay, thank you.